Greetings. I just want to do a short demonstration here with the PhET torque simulation, just to get you to think about some basic torque concepts. So we've got a rotating wheel here. It's not rotating yet because I haven't hit go, but the wheel is 4 meters in diameter, and we've got a 5 Newton force on the edge. So 5 Newton force times 4. Since the force is going to always be applied perpendicular to the disk here, the moment arm, or the perpendicular radius, is always just going to be the radius of the disk, which is 4 meters. So torque 5 times 4 is, of course, 20. So, and there's also a brake, but right now the brake is at 0 newtons. So we've got applied torque 20 Newton meters, 5 newtons times 4 meters. For the torque of the brake, we've got 0 newtons. It's also would be applied at 4 meters, so torque is 0. If we just hit go, so for some reason it always starts going in the clockwise direction. But we see that once it does that, it stops going in the clockwise direction. The blue torque here, or the blue force, causes it to rotate counterclockwise. So a positive torque here is counterclockwise. So now we're going to go with a negative 5 Newton force. And we see that the blue arrow is going in the opposite direction, so we've got a negative torque. Negative 5 times 4 is 20, still no brake. And we can see that the object is speeding up now in the clockwise direction. So positive torque is counterclockwise, negative torque is clockwise. Sorry, I had a brain freeze there for a second. And one way to think about that is using your right hand. So you've probably heard of some different right hand rules, but if you wrap your fingers in the axis of rotation and your thumb points up, that's a positive torque. If you wrap your the fingers of your right hand in the axis of rotation and your thumb points down or into the screen or the page, then that is a negative torque. So let's go back to 5 again and go back to, or not go back to, but have a radius of 2. So now we've noticed the force is now moved in from the outer edge. And we get going. And we can see that there is a counterclockwise rotation, but the speeding up of the disk is not as great as before. So smaller torque means the rate of the speeding up of the disk, also called angular acceleration, is not as great. So it looks like there's going to be some sort of relationship between torque, the product of the force applied and the perpendicular distance to the axis of rotation, and the speeding up rate of the thing that the torque is being exerted on. All right, so one more. Let's this time apply a brake. So this time the brake is going to be applied 4 meters out with a force of 1 Newton. So we can see there was that natural tendency, I'm not sure why the wheel does that, of going clockwise. But then the blue force, the blue torque, the blue force times its distance from rotation, created a torque that then caused a counterclockwise rotation. but notice that wasn't as fast as the time before. The speeding up rate wasn't as fast because we also had a 1 Newton force pointing in the opposite direction. And if you look at the diagram here, you look, well, it doesn't really look like opposite direction because blue is straight to the right and red is kind of down and to the left. But remember, these forces are not causing this thing to move to the left and right. They're causing it to rotate. So now for rotational motion, left and right are replaced by clockwise and counterclockwise. And you can see here the net torque is equal to 6, so 6 Newton meters. So the blue force, 5 newtons applied 2 meters out, that's a torque of 10 Newton meters. The 1 Newton brake applied 4 meters out, that's a torque of negative 4 Newton meters, because this force, if it acted by itself, would cause a clockwise rotation. 10 plus negative 4 is 6 Newton meters. So again, super basic math here, just trying to get you to visualize what happens with torques.